Hi, I am a tutor in Uplatz, and we are going to discuss about C++ programming best practices, tips, and pitfalls. Use of std : I stream under : EOF. Do not use std : I stream : EOF to determine if ELA input operation has failed, as this will not always work. End of fail simply returns end of fail EOF flag for stream. EOF flag for stream can be set during successful input operation when input operation takes place just before the end of fail. When stream extractors operated greater than used fields normally delimited by white space. To read all data in white space delimited field must read one character beyond field in order to know that the end of a field has been reached. If field followed immediately by EOF without any intervening white space characters, reading one character beyond field will cause EOF to be encountered and EOF bit for stream to be set. In preceding case, however, EOF being set does not mean that input operation failed. Only that stream data ended immediately after field that was read. Example: incorrect use of EOF. Example of incorrect use of EOF include IO stream main while true in unitex std : cin greater than x std : cin may be in a failed state. If std : cin dot EOF above input operation may have succeeded, std : cout EOF encountered \n break std : cout x \n. Code incorrectly assumes that EOF will only return true if preceding input operation has failed. Last field in stream will be incorrectly ignored if not followed by at least one white space character. For example, if input stream consists of 3 character sequence 1 space 2, program will output 1 end of file encountered. Example: correct use of EOF to determine if input operation fails. Simply check if stream is failed in failed state. If stream already known to be in failed state and need to determine specifically if failure due to EOF being encoded, then use EOF. Example of correct use of EOF include IO stream init main init x loop while std : cin not in a failed state, while std : cin greater than x, std : cout less than x less than \n. Now std : cin must be in a failed state. Use end of file to determine the specific reason for failure. If std : cin end of file, std : cout end of file encoded \n, else std : cout input error excluding EOF \n. Use of std : endl. std : endl is not some kind of string constant. std : endl is stream manipulated and declared as std : stream and std : and endl std : stream and inserting endl to stream always regardless of operating system equivalent to outputting single new line character \n followed by flushing stream. Flushing stream can incur very substantial overhead, so only fetch when strictly necessary. Use of std : endl continued. Some operating system terminate lines with single line feed character, that is \n, while others operating systems use carriage return and line feed pair \or plus \n. Existence of endl has nothing to do with dealing with adding new lines in operating system independent manner. When stream opened in text mode, translation between new line characters and whatever characters operating system uses to terminate lines is performed automatically, both for input and output. About translation done for all character input output and has nothing to do with endl. Stream extraction failure for built-in types. If stream extraction fails, value of target for stream extraction depends on reason for failure. In the following example, what value of x if stream extraction fails? Unit x std : cin greater than x. If not std : cin, what is value of x? In above example, x may be initialized upon stream extraction failure. If failure due to IO error or end of file target of extraction is not modified. If failure due to badly formatted format data target of extraction is 0. Failure due to overflow. Target of extraction is closest to machine interference level value. Common error: incorrectly assume that a target of extraction will always be initialized if extraction fails for class type. Also dangerous to assume target of extraction always return upon failure. Stream extraction failure continued. Include IO stream, SS stream, LMS C asset, unit main, unit X, std : string stream, SO is 0, X is equal to -1, S0 greater than X. No data X is not set by extraction. Assert is 0 dot file, and then X equal to -1, std : string stream S1 A, X is equal to -1, S1 greater than X. Badly formatted data X is 0. Assert S1 dot file, and then X equal to 0. std : string stream S2 99999, X is equal to -1, S2 greater than X. Overflow X set to closest to machine interference value. Assert S2 dot file, and X equal to std : numerical underscore limits init : max. ABS function. What does the following program output when executed? Include IO stream, include CSTD, lib, init main, std : cout ABS, within brackets -1.5, less than \n. In the preceding code, the ABS function used might be ABS function in the C library, which is declared as init ABS init. In this case, the program would output a value of 1, which is probably unexpected. What does the following program output when executed? Include IO stream, include CMath, init main, std : cout, std : absolute of -1.5, \n. The absolute function used in this case is a overload of the function absolute from the C++ standard library declared as double, absolute double. So the program will output a value of 1.5 as expected. Perhaps the best probable portable correct solution to this problem is to include CMath and use std : absolute instead of ABS. Type of literals means specifying a literal. Be careful to use a literal of the correct type, as the type can often be quite important. For example, what value will be printed by the following code, and more importantly, why. std : vector double values start push underscore back 0.5, values start push underscore back 0.5. Compute the sum of the elements in the vector values. Double sum, std : accumulate values start begin, values comma values start end, comma o. std : co sum \n int. The value printed for sum is not 1. In order to determine what value will be printed, look carefully at the definition of std : accumulate. Answer: the value printed for sum is 0. Testing failure state of streams. Consider I stream or O stream of objects is equivalent to explanation S is equivalent to S dot fail. Bools S is not equivalent to S dot good. S dot good is not the same as explanation X dot fail. Do not use good as opposite of fail, since this is wrong. Member initialization order. Data members are initialized in order in which declared. Example include C assert, class widget, public widget y underscore 42, x underscore y underscore +1, assert x underscore equal to 43, init x underscore, init x y underscore, init main widget w. What will above code do when run in constructor x : x underscore initialized before y underscore, which results in the use of y underscore before x initialization, strictly speaking, undefined behavior. In practice, likely x underscore will simply garbage value when a body of constructor execution on a session will fail. Global object initialization order. Be careful about initialization of global objects. Example, program with 3 source files. Init main include vector std : vector init b is equal to 1, 2, 3, 4. Include vector extern std : vector init b, std : vector init w equal to v of 0, v of 1. No guarantee that v will be constructed before w. Bad things will happen if w is constructed before v. No guarantee about order of initialization between translation units, that is source files, loosely speaking. Implement postfix increment decrement via prefix. Increment postfix increment decrement in terms of prefix. Increment decrement. Ensure that prefix and postfix versions are always consistent. Example, class counter public, counter init count equal to 0 colon count underscore count counter and operator plus plus count underscore return star this count counter operator plus init counter hold star this plus star this return hold. Similarly for prefix postfix decrement private init count underscore. Size of class versus sum of member sizes. Compilers can and do add padding to classes structs include IOStream class widget private character C init I init main two members printer not necessarily the same std : cout size of character plus size of character init size of init size of widget backslash std : cout align half init align of widget. Many processes place alignment restrictions on data. That is a data type of size n must be aligned to start on address that is of multiple of n. Other factors can also add to this. Size of class struct, example virtual function table pointer. Size of class versus sum of member sizes continued. Characteristic padding and use init I. Struct thing characteristic init I. So suppose size of init is 4 and align of init is 4. Implement it adds padding to structure so that init add data mapper is suitably aligned. That is offset is multiple of 4. Division modulus operators and negative numbers. For integral operators, division operator yields algebraic quotient with any factorial part discarded that is round towards 0. If quotient A divided by B is presentable in type of result A/B star B plus A modulo B is equal to A. So assuming B is not 0 and no overflow, A modulo B equals A minus A by B star B. Result of modulus operator not necessarily non-negative. Include C assert, include main assert phi modulo 3 equal to 2, assert phi modulo minus 3 equal to 2, assert minus phi modulo 3 equal to minus 2, assert minus phi modulo minus 3 equal to minus 2. std : string concatenation. What is wrong in the following code? Void func constant std : string and std : string s1 constant character start p equal to 2 func std : string s plus std : string comma plus std : string p func std : string of p plus std : string of comma a plus std : string of s. Unnecessary temporaries fix func s plus comma plus p func p plus comma s plus s std : vector std : string insertion. What is wrong with the following code? std : vector std : string b std : string s 1 b dot push underscore back std : string s b dot push underscore back std : string s plus comma 2 b dot push underscore back std : string 3 b dot push back underscore back std : string. Again, unnecessary temporaries fix b push underscore back s b push underscore back s plus 2 b m place underscore back 3 b m place underscore back. Classes holding multiple resources. What is wrong with this code? Classes 2 resources. Class 2 resources public, 2 resources x underscore null pointer y underscore null pointer x underscore ux y underscore dy. Till 2 resources delete x underscore delete y underscore private x star x underscore y star y underscore. If an exception is thrown in a constructor, the object being constructed is deemed not to have started its lifetime and no destructor will ever be called for the object. So, for example, if the new y throws x and x underscore will be leaked. Fix class 2 sources public 2 sources x underscore make underscore unique x y underscore make underscore unique y private unique underscore pointer x of x underscore unique pointer y of y underscore. Avoid returning by constant value. What is wrong with the following code? Constant std : string get message return allow the constant return value with interact poorly with move semantics as the The return object cannot be used as a source for a move operation since the source for a move operation must be modifiable. Fix std: string get message return allow. Normally avoid using std: move when returning by value. What is wrong with the following code? std: vector init get vector std: vector init b calculate b return std: move b. Due to use of std: move, the type of expression in the return statement does not match the function return type. That is std: vector init versus std: vector init, and then RVO, NRVO can only be applied if the type of expression in the return statement matches the function return type. So RVO / NRVO cannot be applied in this case if the type will not have matched otherwise. Example: a two-element std: tuple and std and a standard std: pair std: move would be reasonable to employ. Avoid returning a R-value reference to an R-value reference parameter. Returning an R-value reference to an R-value reference parameter can potentially lead to very subtle bugs. Examples: std: string and then join std: string and then as constant character star p return std: move dot append comma dot append p std: string get message return allow void func constant string and r equal to join guest message comma word. The lifetime of temporary return by get message not extended to lifetime of r since not directly bound to r now refers to destroy temporary. Fix std: string join std: string and s constant character star p return std: move s dot append comma dot append p. Returning by value, the R-value reference should probably be avoided except in very special circumstances such as std: forward and std: move. No explicit simplet arguments to std: make underscore pair. Never provide explicit template arguments to std: make underscore pair. Let x and y be objects of type capital X and capital Y respectively. What is wrong with the following code? std: make underscore for capital X comma Y. Make underscore pair declared as template class T1 class T2 pair V1 V2 make underscore pair T1 and X T2 and then Y, where V1 V2 are except in special case std: dk underscore T T1 and std: dk underscore T2 T2 respectively. If for some example we are in it, then make underscore pair as two R-value reference parameters which cannot bind to the L values X and Y. Use make underscore pair X comma Y or sometimes pair X comma Y X Y. Prefer use of std: make shared when creating std shared underscore pointer objects. Prefer to use std: make underscore shared as opposed to explicit use of new which shared underscore pointer more efficient. Control back and wound object can be allocated together. One memory allocation instead of two. Better cache efficiency, better exception safety, avoid resource leaks. Proxy classes. Proxy class provide modified interface to another class. Proxy class example include include the class bool vector class proxy for public tilde proxy equal to default proxy and operator equal to constant proxy and equal to default operated bool constant void operator equal to bool of v private friend class bool vector proxy constant proxy and equal to default proxy bool vector star v init I v underscore v I underscore I both vector star v underscore init I underscore class bool vector public bool vector init I colon n of n the new unsigned character n plus 7 by 8 std: fill underscore n d underscore comma n plus 7 by 8 comma 0 tilde bool vector delete d init size constant return number n underscore boot operator init I constant return get elem of I proxy operator init I return proxy this comma I private friend class proxy bool get elem init I constant return d underscore I by 8 greater than I modulo 8 and 1 void set elim init I comma bool b D underscore I by 8 and equal to till 1 less than I modulo 8 or equal to B less than I modulo 8. Init N underscore unsigned characters star D underscore inline void proxy colon operator equal to bool BV underscore set ELM I underscore comma P inline proxy colon operator bool constant return V underscore get ELM IM underscore. Proxy class example can include proxy class underscore class underscore example underscore 1 dot HPP init main bool vector V16 if for init I equals 0 I less than V dot size plus I V of I is equal to I and 1 for init I is equal to 0 I V of size I plus I std colon cout V of I std colon cout backslash n a constant bool vector and CV equal to V for init I equal to 0 I less than C dot size plus I C std colon cout C V of I std colon C1 cout backslash n. C compatibility. C compatibility, although C++ attempted to maintain compatibility with C where possible, there are numerous incompatibility between the languages. Unfortunately, as C++ and C continues to evolve, the number of incompatibilities between these languages continue to grow. In practice, many C programs are valid. C++ program can therefore be compiled with a C++ compiler. Some C programs, however, may require a significant number of changes to a valid C++. A new example of incompatibilities between C++ and C are given in what follows. Conflicts with new keywords include std.io.h, include uni std.h, delete file, init delete, constant character star file name, not function name, return an unlinked file name. Init main, init arg, character star argv, if arg c greater than or equal to 2, if delete argv of 1, print cannot delete file backslash n, return 1, return 0. C++ introduces many new keywords. Some C programs might use some of these keywords as identifiers. Example, new delete. Function declarations without arguments include std io.h, include +1, no argument specified, init main, init C character star argv print, %d backslash n +1 of 0, return 0. Init +1 init I return I +1 in C a function declaration without arguments implies that the arguments are unspecified. In C++, a function declaration without argument implies that the function takes no arguments. Implicit return type include stdio.h, myfunc, implicit return type return 3, init main init C characters star argv init I is equal to my function printf %d backslash I return 0. You'll see if the return type of a function is not specified, it is treated as integer. In C++, the return type of a function must always explicitly specified. More restricted conversions involving void star, init main, init arg C character star argv init I, init star IP, void star VP, IP is equal to and I, VP is equal to IP is equal to VP, problematic, return 0. C provides an implicit conversion from void star to any pointer type, while C++ does not. Scoping rules for nested struct outer, struct inner, init I, init j, struct inner A equal to 1, inner was outer, inner, init main arg C character star argv return 0. C and C++ both allow nested structs type, but the scoping rules differ. Good programming practices, formatting, naming, documenting, be consistent with the formatting of source code. Example, indentation strategies, tabs versus space, spacing, brackets, parentheses, avoid a formatting style that runs against common practices. Be consistent in the naming conventions used for identifiers. Example, names of objects, functions, namespaces, types, and files. Avoid blizzard naming conventions that run against common practices. Comment your code. If code is well documented, it should be possible to ascertain what the code is doing without any prior knowledge of code. Use meaningful names for identifiers. Example, names of objects, functions, types, etc. This improves the readability of the code. Avoid magic little constant. Define a constant object and give it a meaningful name. Constant init max table size equal to 100. std colon vector table entry table max table size. Error handling: if a program requires that a certain constraints on user input be satisfied in order to work correctly, do not assume that these constraints will be satisfied. Instead, always check them, always handle errors gracefully, provide useful error messages, always check return codes, even if the operation function theoretically cannot fail under the assumption of bug-free code. In practice, it may fail due to bug. If the operation is performed that can fail, check the status of the operation to ensure that it did not fail, even if you think that it should not fail. For example, check for error conditions on streams. If the function call can fail, always check its return value. Simplicity: do not necessarily complicate code. Use the simplest solution that will meet the needs of the problem at hand. Do not impose bogus limitations. If more general case can be handled without complicating the code, and this more general case is likely to be helpful to handle, then handle this case. Do not unnecessarily optimize code. Highly optimized code is often much less readable. Also, highly optimized code is often more difficult to write correctly, that is without bugs. Do not write grossly inefficient code that is obviously going to cause performance problems, but do not optimize things beyond avoiding gross inefficiencies that will cause performance problems. Code duplication: avoid duplication of code. If similar code is needed, is more than place, put the code in a function. Also utilize templates to avoid code duplication. The awareness of code duplication has many advantages. It simplifies code understanding, understand once instead of n times. It then simplifies testing, test once instead of n time. It simplifies debugging, fix bugs in one place instead of n places. It simplifies code maintenance, change code in one place instead of n places. Make good use of available libraries. Do not reinvent the wheel. If a library provides code with the needed functionality, use the code in the library. Miscellany: avoid multiple written paths. That is, multiple points of exit in functions when they serve to complicate rather than simplify code structure. Avoid the use of global objects. For example, use static data members instead of global objects. In well-defined code, global objects are rarely needed. Ensure that the code is constant, correct. If an object does not need to change, make it constant. This improves the readability of the code. This also helps to ensure constant correctness of code. Avoid bringing many unknown identifiers into scope. For example, avoid constructs like using namespace std. Only bring identifiers into scope if you need them. Do not rely on undefined and specified implementation defined behavior. Do not rely on any behavior that is not promised by language. Do not rely on undocumented features of library. That is, do not write code in a way that it may only work on certain computing platforms or when the moon is full. Enable compiler warning messages. Pay attention to warning messages issued by the compiler. Learn how to use a source level debugger. There will be times when you will absolutely need it. Be careful to avoid using references, pointers, iterators that do not reference valid data. Always be clear about which operation invalidate references, pointers, and iterators. Testing: preconditions and postcondition. Precondition: condition that must be true before condition is called. For example, precondition for the function that computes square root of x greater than or equal to 0. Postcondition: condition that must be true after function is called. For example, postcondition for the function that removes entry from a table of size n, colons new size of table n-1. Whenever feasible, check for violations of precondition and postcondition for functions. If precondition or postcondition is violated, terminate program immediately in order to help localizing bug. Example, by calling std::abort or std::terminate. Testing: the single most important thing when writing is that it does the job it was intended to do correctly. That is, there should not be any bugs. Test your code. If you do not spend as much time testing your code as you do writing it, you are likely to not doing enough testing. Test should exercise as much of the code as possible. That is, provide good code coverage, design and structure your code so that it is easy to test. In other words, testing should be considered during design. Your code will have bugs. Design your code so that it will help you to isolate bugs. Use assertions, use precondition and postconditions. Design your code so that it's modular and can be written and tested in pieces. The first testing of the software should never be testing the entire software as a whole. Often, in order to adequately test code, one has to write separate specialized test code. Code example: substitution operator for array only class array class. template class T constant T and array underscore 1 T colon operator unit I constant precondition index is in the allowable range. Assert I greater than or equal to 0 and then I less than data underscore dot size. Return data underscore I function taking pointer parameter in it string length constant character PTR precondition pointer is not null. Assert PTR not equal to 0. Quote compute and return string length function that modifies ID complicated data structure void modify data structure type and data structure precondition data structure is in valid state. Assert is data structure valid data structure complicated code update data structure post condition data structure is invalid state. Assert is data structure valid data structure. Finite-Precision arithmetic code example. What do each of the following function output when executed? Void func1 double x is equal to 0.1, y is equal to 0.3, double z is equal to 0.4. If x plus y equal to z, std colon c true, else std colon c false. Void func2 double x is equal to 1, e50, double y is equal to -1, e50, double z is equal to 1.0. If x plus y plus z equal to z plus y plus x, std colon c true, // else std colon c false. False // void func3 for double I x is equal to 0.0, x not equal to 1.0, x plus equal to 0.1, std colon c out allow /n. Number of representation using different radixes. Note all numbers are base 10 unless explicitly indicated otherwise. What is the representation of 1? 3 is in base 3. 1 is equal to 0.3 is equal to 0.13. What is the representation of 1? 10 in base 2. 1, 10 is equal to 0.1 is equal to 0.00112. A number may have representation with a finite number of non-zero digits in particular in a base but not in another. Therefore, when a value must be represented with a limited number of significant digits, the number base matters, that is affects approximation errors. For example, in the base 2, 1, 10 cannot be represented exactly using only finite number of significant digits. 0.00112 is equal to 0.9375, 0.00011000112 is equal to 0.099609375. Finite-Precision number representation only capital or represent small fixed number of digits. Due to limited number of digits, many values cannot be represented exactly. In case that desired value cannot be represented exactly, choose nearest representable value, that is round to nearest representable value. Finite-Precision representation can suffer from error due to round off, underflow, overflow. Two general classes of finite-precision representation: fixed point representation, floating point representation. Fixed point number representation, fixed point representation, radix point remains fixed at same position in number. In the radix point fixed to right of least significant position, it is a format results. It is a format an-1, an-2, a1, a0 dot. If radix point fixed to left of the most significant position, purely fractional format dot an-1, an-2, a1, a0. Fixed point representation quite limited in range of values that can be represented. Numbers that vary greatly in magnitude cannot be represented easily using fixed point representation. One solution to range problem would be for a programmer to maintain scaling factor for each fixed point number, but this is clumsy and error prone. Floating point number representation, radix point is not set at particular position within number. Instead, the radix point allowed to move and scaling factor automatically maintained to track position of radix point. In general, floating point value represents number x of the form s r power e, where s is the signed integer with fixed number of digits and is called significant. E is the signed integer with fixed number of digits and called exponent. R is the integer satisfying r greater than or equal to 2 and called radix. In practice, R typically 2 for fixed R represent a particular x not unique if no constraints placed on S and E. Example 5.1005 under is equal to 0.5, under 1 is equal to 0.05, and 102. Floating point number representation to maximize number of significant digits in significant S and E usually chosen such that the first non-zero digit is significant is to the immediate left of the radix point. Modulus of S greater than or equal to 1 less than R number in the form called normalized, otherwise called denormalized. Other definitions of normalized, denormalized, sometimes used but above one consistent with IEEE 754 standard. 0.75, 0.112, 1.12.2 power minus 1, 1.25, 0.012, 1.012, 2 power 0, 0.05, 0.12 minus 1.02 into 2 power minus 1. IEEE 754 standard, IEEE standard 754, and anyway, most widely used standard for binary floating point arithmetic specifies 4 floating point formats: single, double, single extended, and double extended. Single and double formats called basic format. Radix 2, 3 integer parameters determine value representable in given format. Number P of significant bits, there is precision, maximum, exponent, Emax, maximum, minimum, exponent, Emin. Parameter of 4 formats are as follows: P single 24 greater than equal to the single extended, double 53, double extended greater than equal to 64. Emax 127 greater than 1023, 1023 greater than equal to 16383. Emin minus 126 lesser than equal to minus 1022 minus 1022 lesser than equal to minus 16382. Exponent bias 127 unspecified, 1023 unspecified. With each format, numbers of the following form can be represented: minus 1 power s, 2 power e b0 dot b1 b2 bp minus 1, whereas is belong to 0 to 1. E is an integer satisfying e greater than e min, equal to e min less than or equal to e max. ba belong to 0 1. In addition, can represent 4 special values: plus infinity, minus infinity, signaling a NaN and quite NaN. NaNs produced by operations within at least one NaN operand. Operations yielding indeterminate forms such as 0 by 0, plus or minus infinity, plus or minus divided by plus or minus infinity, 0 dot plus or minus infinity, plus or minus dot 0, plus infinity, plus minus infinity, and plus and minus infinity, plus infinity. Real operations that yield complexes such as square root of negative numbers, logarithm of negative number, inverse, sine, cosine number of number that lies outside minus 1, 1. IEEE 754 basic formats always represent number in normalized form whenever possible. In each case, in such case, B0 is equal to 1, and B0 need not be stored explicitly as part of the significant bit patterns which reserve exponent values, that is, exponent values that lie outside the range of E greater than or equal to E min, less than or equal to E max, used to represent plus or minus 0, plus or minus denormalized number, and NaNs. Each of basic format consists of 3 fields: a side bit S, a biased exponent E is equal to E plus bias, a fraction F is equal to point B1, B2 to BP minus 1. Only difference between formats is size of biased exponent and fraction fields. Value represented by basic format number related to its sign, exponent, and fraction field, but the relationship is complicated by the presence of 0, infinities, and NaNs. Strange combination of biased and sign magnitude formats used to encode floating point value chosen so that non-negative floating point values ordered in the same way as integers, allowing integer comparison to compare floating point numbers. IEEE 754 basic format, single format, 1S 8E F23, double format 1S 11E 52 F. Summary encoding: normal E greater than or equal to min, less than or equal to E max, fraction nil, minus 1 power S, 2 power E, 1 plus F. Denorm, E is equal to E minus 1, F not equal to 0, minus 1 power S, 2 power E min, F 0, E is equal to E minus 1, F is equal to 0, minus 1 power S, 0, infinity E is equal to E max plus 1, F is equal to 0, minus 1 power S, infinity, NaN, E is equal to E max plus 1, if not equal to 0, NaN. IEEE 754 including example, how would the number 5.2 by 10 be represented in single format? 5.2 by 10 is equal to 101.012 into 2 power 0 is equal to 1.0101 to 2 power 2. Therefore, S is equal to 0, E is equal to 210, 127, 10, 2910, 100000012, and F is equal to 0101000, so on 0. Result in the word 0. S is equal to 0. E is equal to 1000001. F is equal to 0101 followed by zeros. Our would the number minus 9.12510 be represented in double format. Minus 9.12510 is equal to minus 1001.001 to 2 power 0 is equal to minus 1 00101 2 into 2 power 3. Therefore, S is equal to 1, E is equal to 3, 10 power 23, 10 power 26, 1 0 0 0 0 0 0 0 0 1 0 2. And F is equal to 0 1 0 1 0 0 1 0 0 0, resulting in the word S is equal to 1, E is equal to 1 0 0 0 0 0 0 0 1 0, F is equal to 0 1 0 0 0 1 0 0 1 followed by zeros. Finite-Precision arithmetic, understand the impact of using finite-precision arithmetic. Do not make invalid assumptions about the set values that can be represented by a particular fixed point or floating point type. Integer arithmetic can overflow. Be careful to avoid overflow. Floating point arithmetic can overflow and underflow. Perhaps more importantly, our floating point arithmetic has a round of error. If you are not deeply troubled by the presence of round of error, you should be, as it can cause major problems in busy situations. Documentation for software development. Documentation plays an essential role in software development process. Many benefits to formalizing and writing various aspects of software at different points in development process. Consider two types of documents: software requirement specification, software design specific description. Software requirement specification (SRS) describe what software should do from external viewpoint. Software design description (STD) describe how software works internally. Software requirement specification establishes agreement between consumer and contractors on what software is expected to do, as well as what it is not expected to do. Can be thought of as a contract between customer and contractor functionality. What does software do? What problem does it solve? External interfaces. How does software interact with external agents such as humans, hardware, as software? Example, command line interface, graphical interface, application program interface. Performance, speed, availability, response time, recovery time of various functional attributes, consideration regarding reliability, availability, maintainability, portability, security, design constraints imposed on implementation against resource limits, operating environment, assumptions upon which requirements are based. As far as continue, distinguish classes of requirements. Essential software will be unacceptable unless requirement conditional would enhance software if requirement met, but not unacceptable if requirement not met. Optional. Class of functionality that may or may not be worthwhile. Should not leave details of software requirements to be determined. Only focus on what the software need to do, not how done. That is, should not describe any design or implementation detail. Typical use cases constraint imposed on software, time constraint, memory constraint, software implementation, restrictions on input data, allowable range for parameters on a method, dependencies on softwares. Example, other programs needed to function. External interfaces, how software interacts with external agents such as humans, hardware, software, command line interface, CLI for program options. Example, required versus optional default settings, standard input, output, error, exit status, graphical user interface, GUI for program window layout, user interaction, example, mouse keyboard action, application program interface, API for library, constant type, classes, methods, functions, namespaces, format, all data used by software. Benefits of SRS: establishes the basis for agreement between consumer and contractor, reduces development effort by thoroughly considering all requirements before starting design, provides basis for estimating costs and schedules, provides baseline for validation and verification, facilitates transfer of software product to new users or machines, serves as basis for enhancement. SRS example: sorting program, single program that performs sorting, given records as input, program sorts records and outputs records in sorted order. Record data format for input-output record delimited by a single unit character. Each record consists of one or more fields separated by one or more white space characters, restriction constraints. May assume sufficient memory to buffer all records. Software must work without any modifications to source code on any platform with C++ compiler compliant with C++ 1.1 standard. Records read from standard input, sorted records written to standard output. Any error warning message is written to standard error. Sorts records using nth field in a record as key. It can sort in ascending or descending order. Sort key may be numeric or string. SRS example: SRS sorting program continue, command line interface, sort -r -k $n -n -k $n, sort using nth field in record. If not specified, n defaults to 1, -n treat key as real number instead of string for sorting purpose. If not specific, key treated as string, -r sort in descending instead of ascending. order if not specified default to ascending order. Give example illustrating expected use cases. Software design description, high-level design, overview of their system, identifying all its components at some level of abstraction, that is overall software architecture, detailed design, aka low-level design, full details of system and its components, example, types, functions, APIs, pseudocodes, etc. Describe high-level and detailed design of software, some context regarding functionality provided by software. How design is essentially structured into constituent parts and roles of those parts. Types and interfaces, example classes and public methods, data structures used to represent information to be processed, internal interfaces and external interfaces not describing as interaction among entities, algorithms. And describe overall structure of software, carefully consider a choice of data structure used to represent information being processed, as choice will almost always have performance implications. Specify any data formats used internally by software, provide pseudocode for key parts of software, state any potentially limiting assumptions made. Benefits of SCD encourages better planning by forcing design ideas to be more considered and organized, allows greater scrutiny of design, captures important design decisions such as rationale for particular design choices, allow newcomers to development team to become acquainted with software more easily, provides point of reference to be used throughout project, promotes reuse of code since well-documented code more likely to be reused, facilitates better software testing since certain types of testing benefit from understanding of software design. SCD example sorting program, key aliases for type that represents sort key, aliases for SCD string, compare functor, class for comparing key objects, data of the set class represents collection of all records, specify all class interfaces, that is public members, data set the class provides, constructor that creates data set by reading all records from input stream, function to output all records in sorted order to output stream, data set class to use STD : multi-map key comma STD : string compare, allow n records to be sorted in order of n log n, time n in sessions each requiring order of log n time, adding n records requires order of n memory, only user C++ standard library. Recommends design document for degree project, documents in combination of SRS and STD with some added information about testing strategies, briefly introduce problems being addressed by software, describe each program and library to be developed, identify parts of any external software example programs or library that will be used, describe user interface, example CLS GUI for each program, fully specify all data formats used, describe all overall structure of each program and library, identify all keys data structure and algorithms to be used, provide pseudocode for key parts of the software, state any potentially limiting assumptions made by software, indicate how programs and library code will be tested, offer any other information that may be helpful since above list is not exhaustive, provide sufficient detail for other people to understand how software is to be structured and how it will be implemented and tested. Limits of knowledge, know what to do, you do not know, ask questions when you are uncertain about something, and be sure that the person who you ask is knowledgeable enough to give correct answer. Know what information resources can be trusted, and use reference materials effectively, example documentation, library standards. Thank you.